So the director of Privacy International said, the defense of privacy will be the savior of the future. Why is privacy so important? So it's a fundamental human right. The Universal Declaration of Human Rights says, no one shall be subjected to arbitrary interference with his privacy, family, home, or correspondence. And it's necessary for democracy. Without privacy, you end up with mass surveillance, you have monitoring and crushing of dissent, voter manipulation from profiling, and eventually swinging of elections. But these days, most of our lives are online. So if you want to protect privacy, you need to protect privacy online. So let's have a look. What happens right now when you visit a website? So the first thing your browser does is a DNS lookup, which sends the site that you're looking up to whichever DNS server you're connected to. You then make a TLS connection to it, which involves trusting about 140 certificate authorities in your browser. If any one of those is compromised, it's game over. You have the connection to the server. You then load arbitrary code, whatever the server returns, basically. And then most websites will then have some third-party sites which are included. So you then do the same thing again, but with a bunch of third parties, sometimes lots of third parties. Some sites you will log in, so you'll give them a username and a password or something like that. And typically you'll then be storing some data there, so you send them some personal data, which may or may not be encrypted. Typically it won't be. And if it's some kind of a social site like Facebook or Twitter, then there's some kind of a social feed with an AI algorithm which is controlling what you see. And that's the thing that can lead to manipulation into, because the AI is not operating in your interests, and eventually leads to subverted democracy. So could a better design fix these problems? Obviously, I think the answer is yes. What do we think are the requirements of such a thing? So we want to protect against third-party surveillance, for sure. And ideally, actually, first-party surveillance. That might sound a bit weird, but it is possible. We want to remove the incentives that resulted in surveillance capitalism being the dominant business model on the web. And to do that, you have to return the data and identity ownership to the end users themselves. So you should be able to take your data between hosts and between apps, and it shouldn't matter. It should just work. And it should work in existing browsers. So this was the motivation for us to start work on Peergos in 2013. Something else happened in 2013 which triggered us, but you may be aware of. So Peergos is a global end-to-end encrypted file system. Has fine-grained access control to individual files or an entire subtrees and directories. Critically, it has signed content addressed. Everything is signed and content addressed. So when you're retrieving data, you don't have to talk to a particular host like the current web. So this allows you to do things like automatic host migration. So if you have a server storing your data, you can move to a different one, and all the links, all the pre-existing links to your stuff just continues to work because the links aren't based on identity, they're based on content. And in the foundation of the file system, there's a concept of identity, and this is portable and self-sovereign as well, so it's host independent. And the final thing is we have a sandbox for apps, which is the thing I was talking about for loading arbitrary, untrusted content. So the basic architecture is just a standard peer-to-peer architecture, a sea of nodes. All communication between nodes is encrypted with TLS or noise, but critically it's TLS, but there are no certificate authorities or DNS. And this comes about because each node is addressed by its public key. So you know their public key in advance, so you can just put that into the TLS connection without having to refer to any certificate authorities. And basically, if you have someone's public key, someone's server's public key, you obviously need an IP address to dial them. So you have to find that somehow, and typically that's using a distributed hash table. But there are other ways to do that as well. So I've mentioned, yeah, so trustless servers, all blocks are content addressed, and when you get something from the server, you verify the hash. I should specify that's what content address means, is you have the hash of some data and you say, give me this data to whoever. They give you the data, you then hash it locally yourself and check that it is what in fact you asked for. And the whole idea of cryptographic hashes is that the data can't be tampered with. So you know that you got exactly what you asked for. Now that's okay for immutable data that doesn't change, but most data does change. So you want to be able to sign updates, and you do that with a public key where you sign a new hash, basically. And on top of this, we have the PKI, the public key infrastructure, which basically just gives you human readable names, because people don't like to remember public keys in URLs and things like that. So the end result is you get location independent addressing or server freedom. So let's talk about the identity. So it's a mapping from username to mostly two public keys. So one is your identity public key, so that's your identity on the network, and the other one is the identity of your current home server. And the PKI, it's an append-only Merkle log of signed name claims. It's similar to certificate transparency logs, if you've heard of that, which are used for normal TLS certificate authorities. And the data structure we store this in is called a compressed hash array mapped prefix trie, or CHAMP, which is a bit of a mouthful, but it's a super cool data structure. We'll talk more about it later. We use it in a bunch of other places as well. So as far as properties of the identity goes, so I've mentioned it's host independent. It's TOFU, or trust on first use, in terms of if you're friending someone, but you can also verify in person if you want with a QR code or over the phone or reading out the number, and that just uses the exact same algorithm that Signal uses. So what happens when you upload a file to this thing? So you take the file, you split it into 5 megabyte chunks. That's important for a reason we'll see in a minute. Each chunk is independently encrypted, and that's then split into up to 5 1 megabyte blocks. And then those are uploaded, and you then also add some encrypted metadata, which refers or references those blocks. So the encrypted metadata is it's called a Crete tree node. So this is what your file system looks like. So this is a CHAMP. So it's an immutable data structure. So it's used in functional languages. So Scala uses it for maps. The only difference in Scala, the links are just pointers in memory to immutable objects, but in our case, the links are hashes. So they're Merkle links between blocks. And so yeah, it's a key value store, and the values in our case are Crete tree nodes, and they can reference up to 5 encrypted file blocks. So yeah, so the CHAMP, let's talk a bit more about that. One cool property of it is it's independent of insertion order, unlike a B tree. So if you have the same set of mappings and you put them into this structure in any order, you always end up with the same Merkle root, the same hash. And it's balanced as well. So in the Peergos file system, the keys we use in the file system CHAMP, they're just random 32-byte labels. So they don't actually have any meaning. In terms of the metadata, so we care a lot about metadata. So remember I said the files are split into 5 megabyte chunks before, and those are separately encrypted. The way we store them in Crete tree, the different chunks of the same file aren't linkable. So you can't see the size of a file, basically, or indeed that those chunks belong to a file. And even within a chunk, before encryption, we pad any data to a multiple of 4K. So you end up with 5 meg divided by 4K, which is 1280 possible chunk sizes in the entire world. So there's not much entropy there to figure stuff out with. So your server can't see the file sizes, can't see even if something is a file or a directory. A directory just looks like a small file, basically. And obviously the file and folder, the names are encrypted, padded and encrypted, so you can't even see the size of the file name. You can't see your folder topology, your social graph, who your friends are, and your server also can't see who or how many people have access to a file or blog. So one of the guiding principles here is some people will want to self-host, but most people probably won't, because that's just how things work. It's harder. Most people will probably want to pay someone else to store their data for them. But we wanted to have it so that there wasn't any significant privacy benefit from self-hosting. So you're perfectly fine to pay someone else to do it, and you don't need to trust them. So this is the crypt tree format, what one of those crypt tree things look like. The 3 green sections are encrypted sections. The number on the right just means it's padded to a multiple of whatever, 64 or 16 or 4K, the one I mentioned. The thing at the top, BATS, stands for block access token. It's just a way to do access control to the raw ciphertext. We'll talk more about that in a minute. I'm going to come back to this slide. So this is the read crypt tree. This is where the name comes from. It's a tree of keys for access control. So each directory or file has 2 symmetric keys. And the idea is if you have one key, then you can follow the links to in the direction of the arrows to derive all the other keys. So if you have the base key for this first directory, then you can read the entire subtree. If, however, you only have what's called the parent key for the file, then you can read the file's metadata and its data, and you can follow these links back to basically get the path. So everything has a well-defined path, but even if you can read that file, you can't read any of the sibling files in the same directory or even see how many there are. And so yeah, so that's enabled by in this from parent thing. There's this parent link. That's the backlinks you saw. There's the file properties, which is the name, the size, modification times, sometimes a thumbnail. Yeah. And then let's jump here. Okay. The right crypt tree is a bit simpler. There's just one symmetric key for each file or directory. And if you have that key, then you can derive the key pair, which is used to authorize writes to that section. So you can split off subdirectories into different signing spaces, which means there's a different authority for modifying them. And the server obviously enforces those, but you also check them when you retrieve them. So the server still can't mess around with it. So capabilities. So this is all based on capabilities. The idea is a capability is pure information. It's not identity based. It's not saying this person can access this. It's like a password. It's saying if you have this capability, you can do this thing. And so we've kind of talked about read and write capabilities, which are enforced with the crypt tree structure. The one thing where the server does is, so the read and write access is enforced by maths. Your server doesn't need to enforce that. What we call the mirror capability, the server does need to enforce that. So mirror is just access to the ciphertext. So if you have a mirror capability of something, all you can do is retrieve the ciphertext, not even for a whole file, just for a blob. And so a server already has all the ciphertext because they're storing it, right? Your server. So they inherently have mirror capability to all of your stuff. And in terms of what's actually in a capability, so the mirror one, it has the first two, the owner and the writer, are public keys. And then the map key is just to look up into the chant that I mentioned, the 32 random bytes. And there's the BAT, which is another 32 bytes, when you talk about that. And that gives you, that's enough to retrieve the ciphertext. And then if you also have the read key, that's again another symmetric key, then you can decrypt it and read it. And if you have, in addition, the symmetric write key, then you can then modify it. And so this is the kind of 3 different levels of capabilities that we define. And you can revoke capabilities by just rotating the keys, essentially. And because it's identity-based, it means it works in secret links. So you can put a capability into a link, and the link will just work and be able to resolve whatever it is. So let's go through what actually happens when you resolve capability. So first thing you do is you use the PKI locally to look up the owners. So you remember the first thing in the mirror was the owner. So you look up the owner's host peer ID or public key locally in the PKI. So that's basically the kind of the address of their home server. So then you do a peer-to-peer HTTP request to that home server via the public key, and you get the mutable pointer for the writer. So a mutable pointer is this thing at the bottom, which is basically a signature over the previous root, the previous hash, the current hash, and a monotonic sequence number. We keep the previous root in there so the server can enforce hazards, basically compare and swaps. So whenever you do your modification, you sign it, and you know the version of the thing that you modified, and so that's then included in the update, and the server can check that you're not, if there are 2 concurrent updates, one of them will fail, basically. They can't overwrite each other. So then you've done this peer-to-peer HTTP request, you get the pointer, you verify the signature, and extract the root hash from it. Then you do another peer-to-peer HTTP request, or you can do it locally if you already have the blocks, to do the champ lookup. And all that does is return the blocks from the root of the champ up to the crypt tree node, including the crypt tree node. And once you've got those blocks, you repeat that champ lookup locally, and you use the read key to decrypt the crypt tree node and get the metadata. So then you've got the metadata, then you've got the references in the metadata for the blocks for that particular chunk. So you can then go and retrieve them using the bats. For each one will have its own bat, and retrieve them via the hashes in the crypt tree node. You can concatenate the blocks and decrypt it, and then you've got the data for that chunk, that 5 megabyte chunk of the file. So then you need to calculate the next chunk. So the lookup key, the map key in the champ for each chunk, you derive the next one basically by hashing. So there's this thing called the stream secret, which is in the first chunk of a file. It's again 32 random bytes, and you're basically hashing that with the current champ lookup key, and that gives you the next one. So you can iteratively just hash to derive subsequent champ lookup keys. So you repeat that for however big the file is, for however many chunks you want to get. So one cool thing that you can do because of that design is fast file seeking. So when we first wrote Peergos, we didn't have this idea of deriving the next label from the current one. All labels were just random, and basically it was an encrypted linked list, which works until you had like a gigabyte movie and you wanted to seek near the end or something like that. And then you would have to do a lookup, get every single crypt tree node for all the chunks along the way, which obviously is slow. So yeah, this was done to avoid that. So now, once you've got the first chunk of a file, you just do a bunch of hashing locally. So you then derive the map key for however far along you want to seek, as well as the bats. So the bats are derived in a similar way. And then you can just, so a bunch of hashing and then a single request basically to get the thing you're actually looking for. So it ends up being much faster. So now let's try that in a demo. Sound on? Is the sound on? We'll find out. Okay. All right. So this is a movie here. Can you see? Yeah. So this is Simtail. It's an open source movie. So you can see it starts playing relatively quickly. This isn't a gigabyte. This is only 100 very fast.
I have been waiting.
Backwards and things like that. And yeah, so while we're doing that, that's all, it's end-to-end encrypted. It's decrypting it locally. It's doing that hashing trick to seek forward. And the server doesn't learn that those things, apart from maybe timing attacks, that those chunks are connected. Just cool. Very good. Right, so I said I was going to say more about bats. So the basic idea here is, sure, you can encrypt data, but even if the data is encrypted, you shouldn't make the ciphertext public. So bats give us a way to do post-quantum ciphertext level access control. There are 2 bats for each block of data in the system. And the whole system is based on S3v4 signatures, so it's the same author S3 uses. And it's tied to the requesting server. So you ask a server to ask the whoever has it for it. The request that is generated from the bat, the auth is tied to that server, and also the time. That's just standard S3. And the recipient verifies the signature against the requesting server's peer ID, which it knows from the connection, because they're by authenticated connections. And one cool property of this is kind of auto scaling. So if you say you have a popular video or something, and thousands of people view it, and their servers or whoever they're accessing it then have copies of those blocks. They can then continue to. They can then serve up those blocks and apply the same authorization. So because the bats themselves are in the block. So once you have a block, you can read the bat. It's just 32 bytes somewhere in it, and so they apply the same access control, and so it just scales with however many people have it, basically. So the 2 kinds of bats. There are inline bats, which are directly in the block, which I was just referring to, and they're just random. The second bat is called a mirror bat. That's kind of a user-wide bat, and that's not referenced. That's not directly in the block, but it's referenced by its hash. And the idea there is that gives you a single capability you can give to a server which you want to mirror all of your data, your entire file system, still without being able to read anything. So all the blocks are one of 2 formats, either CBOR for kind of non-leaf nodes, or raw blocks for the leaf, the encrypted fragments. CBOR blocks, it's easy. It's normally a map. So you just have a top-level entry in the map, which is bats, which have the 2 bats in it. The raw blocks, we had to put this magic prefix on the front, which, if that magic prefix is there, then you just read the bats off after that. Because blocks don't have to have bats. If a block has no bats, it's implicitly public. Cool. So let's take a step back and go back to the actual login process. So you have your username and your password, and there's a 32-byte salt which goes through script with quite hard parameters. And the output of script is 2 things. There's a login key pair and a symmetric key. The login key pair you use to auth with your home server, which then gives you your encrypted entry data. And then you just decrypt that with the symmetric key, and that gives you your actual identity. So your identity key pair, a thing called your social key pair, and the root capability into your file system. And because it's a tree, it's recursive. Once you've got the root dir capability, you can, and it's obviously a write capability, you can do everything. And the key thing, so there's two things here to protect you. So one is to protect people who use silly passwords. Obviously they shouldn't, but they will. So that's this step here, all through the home server, that can be rate limited, obviously, because that's talking to a particular server. But if someone hacks the server, say, and they get access to this encrypted entry data, then your protection falls back to how fast you can hash with script, or try passwords through script. And our basic idea is that humans shouldn't create passwords. So we have a built-in password generator. It just picks 7 random words from 2048 words. So that gives you 77 bits of entropy. And if you do the maths, so a GPU can calculate about 1 million script hashes per second. That's actually on using easier parameters than we use, so this is a conservative estimate. So one GPU would take about 5 billion years to crack one of these random passwords. If you had 1 million GPUs, which some people do these days, then it would still take 5,000 years. And yeah, depending on your threat model, this is the graph of, so this is the cost to crack a password in 10 years, which is probably within most people's threat models. The y-axis is log-based 10, it's logarithmic, log-based 10 of the cost. Units don't really matter, but it's US dollars. You can see the green line is the NSA budget, annual budget. And so we've picked the circled one with seven words there. You can probably be okay with 5 or 6, but that's what we went with. But you can change it if you want.
Yeah. Before we move on, can you talk about the home server maybe? Is the home server like a different entity to the rest of the network? Is it just what?
It's the same thing. So when basically your home server is the server you sign up through. So it could be local, it could be a local thing you're running, or it could be some other server. But because of the stuff at the beginning, you can migrate automatically, like with a command, to another server, and everything still works. And yeah.
Okay, so there's a home server, and if you migrate somewhere else, then that becomes your home server.
Yeah. So the migration process basically tells the new server to first mirror all your data, and then once it's got all your data, you then update the PKI to basically flip a switch to point it out. And you can do that unilaterally. So if your old server, if you have a copy of all your data somewhere, if your old server disappears instantly, you can start a new server with your data and portably update the PKI to say, this is my server now. So you can't be held hostage by your old host, your original host. So I haven't talked about the social side of things yet. I said there was a social key pair you get when you log in. Basically, that's used to send a follow request. So what you do when you send a follow request is you create a new directory just for that user in your space, which is your channel for sharing stuff with them, for sharing capabilities. And you encrypt that capability, you blind it with an anonymous key pair, and send that as a follow request, which is basically stored in an encrypted inbox, which they then retrieve and decide whether they want to accept that or not. And they can reciprocate and make it bidirectional. And then you have one-way encrypted channels, possibly 2 of them, but and then anything else you share goes through that channel. So the other thing that hasn't been talked about at all yet, the application sandbox. So our goals here were to run untrusted code over private data, such that an app can't exfiltrate data. So you can run it over all your private data and it can't steal it. Which I'm not aware of anything that does that on the web, at least at the moment. The app can't read anything it's not granted access to explicitly. and it works in existing browsers without extensions. It also works offline. Apps have a simple REST API without a server. What does that mean? What is an application? It's in Peergos. It's just a folder of HTML5, basically. The author controls visibility. It's just a folder in Peergos, so you can card for access or something if you want, out of band or make it public or whatever. There are some basic permissions that apps can request and you can grant. These are probably going to expand, but we've got about 5 or 6 now. You can register, an app can register for certain file types or MIME types, so like an audio player or an image viewer or something. And it's super easy to publish. It's a folder you just drag and drop. And a website that doesn't have any permissions is basically, an app that doesn't have any permissions is basically a private website. So it has its own assets, which are HTML, and it can render those, and that's it. So one special app we have is a kind of a browser app, which kind of does that. It just renders other folders of HTML, and it isolates different folders. You can have internal links within the page or external links to other stuff in Peergos. It works in secret links, and you can have markdown pages as well. So this is how the architecture is for the apps. So you've got the main Peergos tab that you log into is on the left. So that would be peergos.net, or you can run it locally. So this can be localhost as well. It works on localhost. And then when you run an app, we load it's a hash, but a random subdomain. And what the server serves up the same static content for all subdomains. And all that static content does is set up a service worker and then initiate loading the app's assets via these are post messages between the two contexts. And the reason for this is that the app is then isolated from the main context, so it's in a different OS process, so it can't steal whatever passwords from memory or keys or anything. And it's locked down with a CSP firewall so that it can't exfiltrate data. So it can't make any external requests to the web or anything else. All it can do is send these post messages back and forth to the main Peergos tab, and that's where permissions are enforced. So what kind of things can an app do? So you can edit files. So we have a word processor. There's a spreadsheet, an image editor, markdown editor, Piddlywiki notebooks. You can have like a media player I mentioned. There's a Winamp clone. Multiplayer games, that's starting to get interesting. Chat. You can play Doom if you want, as always. There are a bunch of example apps we've got an example -apps repo in Peergos on GitHub. I'll show that again later though. So I mentioned, the app structure, you've got your HTML5 assets in an assets folder. And the only other thing is this file, this manifest file, it's a JSON file, which has a bunch of metadata about the app. If there's one of the permissions is the ability for an app to persist data into your Peergos space. So it's a bit like an Android or whatever mobile app that can store data on your phone. So it's private to the app, so no other apps can read it. But it's a way to persist state in some way. So this is what a typical app manifest looks like. So you've got a display name, version, whether it's launchable, what kind of extensions or file types it can do, and the permissions it's requesting. And in the extensions and file types, you can put in wildcards and stuff like that. So these are the permissions we have at the moment. So the one I mentioned, store app data to persist data. You can edit a chosen file, and then with that, if you open a file with a given app, it gets write access to that particular file temporarily, and as long as it's open, basically. You can have read access to a folder, More interestingly, you can exchange messages with friends. So that's how we do things like the multiplayer games, and chat works over that. And recently we added access profile photos. So that's not just your profile photo, but profile photos of your friends as well. So if you have some kind of social app, basically. You can pass various parameters to it, like the theme and whether it's writable, so an app can adjust what it thinks it's doing, if it has write access or not. So the REST API, I mentioned REST without a server. So basically, you remember we, what slide is this? 56. So yeah, so this service worker thing that was set up, the app can make standard HTTP requests, but they're intercepted by the service worker, which then translates it to a post message, which is then sent back and handled and replied that way. So there isn't actually a server per se in that case, even though it's a REST API.
But in the app code, it is just standard HTTP requests.
Yeah. Yeah, so they don't know that they're in this little sandbox thing. Yeah, so there's the API to get private data, app-specific private data. You can post an HTML form and store the results. That's the chat APIs under that. As far as the file API goes, you can get a file or a directory. So this could be your assets or in your anything you have access to, basically. You can ask for a preview to get a thumbnail. You can create, update, delete, append to files, the usual stuff. The chat API is slightly interesting. So you can list all the chats created by this app. You can create a new chat. You can get messages from a given chat, and you can obviously send a message. Now, a message could be anything. It's just data. It could be a move in chess, or it's not at the moment. It's not really real time. I would say it's asynchronous. What we hope to add in the future would probably be under a new permission. Would be kind of like a real time stream, which would be appropriate for like streaming video or something like that, or real time game. Right, demo time again. Right, so I'll just demonstrate a bunch of some of the stuff we have in terms of apps. So there's a docx viewer. Oh, that didn't work. Sorry, I double clicked on that. I need to change that shortcut. Viewer, there we go. Oops. Got there in the end. So that's just a Word doc. I don't know why I couldn't know. Are you seeing that pop up thing? So there's an image gallery. I mentioned spreadsheets. There's also a PDF viewer, which is probably the most locked down PDF viewer in the world. There's a notes app, so you can write kind of notes, which can have inline images or LaTeX or mermaid diagrams, all that kind of stuff. So as far as the website, so this is, as you can see, this is just two files, an index HTML and an image, and we can just view that, and that's loading in a sandbox. One thing I didn't show, I mentioned profiles and profile pictures. So you have a profile here, which yeah, so it's got a bunch of fields. Now, On wiki. So there's also a text editor, which is supports all kinds of languages, Markdown, whatever, Go, Java. There's a recipe. So that's a viewing of it. You can, and if you edit it, you get a different view. Cool. There's also a media player, so you can play music. One cool thing we do is if you upload MP3s, if there's any cover art in the MP3, it will extract that and make it the thumbnail automatically. There's one example there. Cool. All right, can we switch back again? Yep.
For the application that publishes a website from the content that, no, let's say, is it an application or it's embedded on previous server?
So what you're doing when you do that is you publish a capability to your website in a publicly lookupable place. It's still in Peergos. And then any gateway does that trick of getting the username from the domain name and looking it up via the PKI and finding that capability and then getting it and just serving it like a normal website. So the gateway does the Peergos specific part, and it's all just the website after that. Your website.
In that case, you do need TLS and DNS.
Yes.
Yeah, to get to the gateway.
Yeah, just to get, unless you're running on localhost. Yeah.
Right. Okay. So if you set up a local gateway, then you.
Yeah.
Okay. So can you just run the gateway locally and then, talk to other Peergos servers?
Yep. Yep. So the way we run Peergos.me, it's running a gateway, but it's using Peergos.net as its Peergos server.
When you upload your content, because for example, it's following its own way of storing things. So, for example, for a movie, do you need only the embedded? The only way to view the movie is via the embedded media player, or you can stream it somehow based on either online system players or.
In Peergos itself, there's a built-in video player. There's also, you can write your own one as an app. Any app can do it.
As an app.
Yeah.
Because this taking as well should follow the rhythm.
Yes. If you're talking about the public website bit, then that's just a normal web server. So normal, like the browser would do a range request. The server will interpret that and do the seeking server side. Yeah.
And is there a way to?
Well, hang on. Yes and no. So you can share a secret link to a video, and that will just open it like in any browser. So you don't need to install anything.
And is there the opposite direction of data? I mean, instead of uploading and following all this, to be able to download something, let's say in normal file, back again and use it as shipping.
Yeah, so everything is just a file. I think that's what you're asking.
Download it, right?
Yeah, you can download your entire thing. Yeah.
To use it outside the previous.
Yeah. So the only thing you would lose in there is the metadata. So if we had like a thumbnail, for example, I mean, hopefully that's generated from the content itself, but that's outside of the file itself.
Is it possible to look it down directly? It's context.
Yeah. So in the UI, you can download an entire subtree as a zip, and it will just stream it to a zip file. Right. So yeah, a couple more cool features. Offline login. It's not normally a thing, but because of the design, if you've have selected well, once you've logged in once on a device, you cache that encrypted login data that you had to retrieve during the login process. And so then you don't actually need the server to log in. So once you've done it, logged in once on a device, you can then log in again totally offline and read. You can't modify anything, but you can read anything that you have cached locally, which is kind of cool. And there's a thing we do when you're using Peergos, as you're browsing around. Every time you change directory or open something, we update the URL with basically the path where you are, and if something is open, its name and the app it's open with, but encrypted. So the URL is just encrypted data. But it's kind of like a deep link into Peergos. So the idea is we're not leaking anything to your browser history, but you can bookmark these things. And if you log in through one of these links, it will take you back where you were and open the thing that you had open with the app that you had it open with. It's just a neat thing. So one of the things we care about is sometimes your device is in the threat model. So things like Signal basically assume all bets are off if someone gets access to your device. Whereas the approach we take is as long as you're not logged in, then someone shouldn't get access to anything. So they'll be able to see any ciphertext you have cached, but that's it. And even with that, we still get this offline login thing. So yeah, some cool things. The other thing, I didn't show this. Maybe I'll show this afterwards. There's a social media kind of app in Peergos, which it's kind of what you expect from a UI in social media. You can make posts which can have images or videos or text. People can comment on them. You can comment on comments and so on. But our belief is that public social media is bad for society for a couple of reasons. So it allows micro-targeted political profiling. So certainly something that's literally public, like Twitter, and to a lesser degree, Facebook. And because of that, it's open to abuse. So yeah, I mean, there have already been certain elections that have been swung using advertising on certain social media. But really, I think the concept of public is a bit like infinity. Nobody really understands it fully. Insofar as once something is public, you can't really take it back, like information theoretically. And so, most people are not going to think, 5 years down the line, someone will be feeding this into an AI that I'm not okay with, or something like that, which is happening a lot now. So the way we wanted to design the social media is it's end-to-end encrypted. And so when you make a post, you can choose the audience among people who are following you. And if someone comments on a post, then that person's comment is basically visible to the audience of the parent post. So it's kind of modeled on real conversations. So like if you're at a party or in a room, you're talking to someone, and the people, and as a part of that conversation, can hear it and reply and so on. But no one, at least for most parties, the rest of the world can't hear it. So that's the idea. And yeah, so I'm just finishing up. Without privacy, there can be no democracy. So, any more questions? Yep.
I think you forgot to mention something. Was where's the catch? There has to be something that doesn't work as good as it should.
Some things. Some things are slow. This would be my thing. Where there's still a lot we can do there. I mentioned we started in 2013, so we've been working on it for a long time. And actually, the last week, someone logged in and we have a public chat, Peergos chat, and they said two people independently actually said that they hadn't logged in for a few months, and it now looks 20 times faster to them. It's not. I don't think it's actually 20 times, but it is faster. And there's still more we can do there. It's just a matter of priorities.
You talked about the CSP firewall, but if I'm not mistaken, this is something new in the browsers, right? Or is it something established?
CSP has been around for a while. This is CSP 3, so you do need modern browsers. Okay. There's another reason you need modern browsers is the thing we use to do streaming via these post message things, like if you're just playing a video or something, uses writable streams, which Chrome has had for years, but Firefox only got it a few years ago, and Safari, I think, 1 year ago. So yeah, you need fairly recent browsers.
Okay.
What do you, so I mean, we saw there are like notes editors and like text editors and image editors and like a bunch of apps. And I'm wondering, what do you lose if you don't use the inbuilt apps, but you use like, you know, your usual apps, and then you just store the files in Peergos, the resulting files of the app? Why would someone prefer to use the inbuilt, like the apps within Peergos?
Maybe convenience, because you have to install the native app. The native app won't be sandboxed.
Okay.
So it could exfiltrate stuff.
Right, so you have to trust the app, whereas here you only have to trust, like, you know, Peergos,
Yeah.
which is.
Also, suppose that you will have to download the file itself and reload it, right? Which means that you generate a file.
Yeah.
Different URL.
Okay. Yeah. Well, I mean, files have the same sort of human readable path. It's just a normal file system. But
Speaking of file system, could we mount
yes,
like Peergos or the files we have stored? Can we mount them and access them as like a?
yeah. So at the moment we have a fuse mount, which definitely works in Linux. It used to work in Mac and Windows, but Apple have been making it harder and harder. What we're probably going to do is implement WebDAV, and then that should be more universal. And yeah, Mac or even on mobiles, I think that will work.
You mentioned earlier about caching. Does this thing caches chunks or files itself? Because if you cache the chunks, it will be almost impossible to have a real time access to it when you're offline, right?
So we cache the raw encrypted blocks in the browser.
Do you have any options, anything that you could mention? Look, I want up to this size to cache files, or this file or this will be cached, and so on.
So yeah, people have asked for basically like a access offline thing, and you would mark a file and say, I want to view this offline. At the moment, it's just kind of an LRU, so it's the most recently used stuff. You can set the size of the LRU in terms of megabytes, but yeah, we probably will eventually add that. Like, I want this thing on this device offline.
So even if you run Peergos locally, in that case, you would have the files offline, right? Because it's just running on your machine.
If that's your server, yeah.
Okay.
It doesn't have to be your server. So you could use Peergos.net could be your server. You could run Peergos locally, log in through localhost to Peergos.net, and then your local server is acting as a cache. You could also tell that local one to mirror using a mirror capability to mirror your entire file system, and then you would have everything offline, read only. You still need rights need to go to your
Yes.
actual server.
Yes.
But cool. So
So I have one more.
Yep.
You mentioned, like, before you mentioned, third-party surveillance and first-party surveillance. What was that? What is that?
So there is no third party basically. So in terms of apps, unlike a website that can reference a bunch of other content, apps have to be self-contained. And I think the web is kind of moving this way anyway, like with blocking and third-party cookies being blocked and so on. So there's a limited benefit from external third-party stuff. So basically, yeah. So an app is 100% self-contained. So there is no third-party possible at all. First-party tracking is possible depending on. Well, it is and it isn't, because everything can be stored.
First-party tracking?
So yeah, exactly. So first party would be, so comparing it to the web, if you're viewing a website, you're talking to that server. So that's the first party. So they know that you've connected at this time from this browser and da da da. So we're already better insofar as there's no HTTP request to a server, so they don't see your browser or any of that stuff. And indeed, they can't, the JavaScript running can't send anything back. So there's no like fingerprinting, for example, or anything like that. So that part's all gone. You still need to get the assets themselves, but that's, again, because it's host independent, that could come from anywhere in theory. You could have a cache, and every time you access it, you talk to that rather than the server. So yeah, most of the first party tracking is gone as well. Yeah. Another question?
So in terms of performance of distributing these files, how that has been behaved, because you mentioned earlier that chat isn't so responsive, so real time. So we suppose that it follows the same principles that files used to share between nodes.
Yeah, so the way chat works, chat is basically a single chat is basically a file of, and it's an append-only log of messages in Peergos. So when you send a message, you're just appending it to your copy of the chat, and the other chat members have their own copy. And so the messages aren't necessarily in the same order in different members' copies of the chat, but it's still in a causal order. So you merge in new messages before you reply to them, so kind of thing. Sorry, where are we going?
In terms of performance, how does
Right.
how is this possible? How does Peergos can, let's say, in your example with chat, how can it be assured that it achieves if I write a comment, if you write a comment at the same time, how this will be distributed?
So yeah, so the reason why chat is a bit slow is, as I say, so you append, when you send a message, you append it to your own chat. That's it, you're done. There's no like notification or anything like that. So the other people have to basically poll, the members of the chat have to poll your copy to get the latest messages. So it's just how often is that polling basically. In the future, we would actually like to have kind of a direct signaling mechanism, at least if you're like connected at the same time kind of thing, to say, there's a new message here, you need to pull it. Not actually sending the message, but just like a trigger to update. And then that would be basically real time. But we haven't done that yet. But yeah, phone files themselves is it's kind of a different mechanism. I mean, a chat is a file, but it's this noticing updates that is the reason that it's slow. Whereas if you just have a file and you're just trying to send it, there's no real limit.
Would you be able to transfer the ownership of the file system that's created? Trustless mode.
Depends what you mean by transfer ownership. You can
So the rights, the ability to access all that.
So you can grant write access to things, or you can grant. I mean, you can share read or write access to anything. That doesn't change the owner though. that just gives them write access. So the owner is always the same thing.
You can't transfer the ownership.
No. I mean, I guess you could always copy the files or in some way mirror them.
Could you grant someone mirror access if they could like copy the files and then they would be owners of these same files?
Well, if they mirror some data, they're still not the owner for it. So the owner is basically, from the file system perspective, is the kind of the top level directory. So you might have noticed in the demo account, all the paths started with demo. So that the first element in the path is your username. Yep.
Could this be used like with together with like IDEs to write code? Do this like require too many accesses? It's not like just edit.
Yeah, no reason why not. I've only edited personally individual files in there, but I have tried uploading a Git, like a big Git directory, Git repository, which we had to do some optimizations to make okay. But yeah, lots of small files.
Is it easy like if someone decides, okay, I want to try it and then like opt out, like and decrypt everything is possible?
Well, you can always just download your files. So you can any directory you can just download it as a zip, and that's plain text, whatever.